Why do we move around? Well, mostly we're after something. We either need to get something to eat, to have sex. We need to do some kind of motivated behavior. And that behavior usually comes about because there's some reward that we're seeking. And we often take our complex motor movements for granted, but in fact, if we try to get a computer to simulate them, it's quite interesting. So let's take a look here at a clothes folding robot. This took probably millions of lines of code and the efforts of top scientists and engineers in order to do the simple task that you probably did this morning in your kitchen. So the robot is able to straighten out the cloth, fold it. I like the way he pats it down. And I don't know if this robot can fold more than this one particular size of cloth, but you can fold any type of cloth size you want. Your brain is very flexible in its ability to change motor activity for a particular situation. And of course, what we do is we develop certain motor programs. So as infants, we're given a cup. For a long period of time, we need to use two hands. And then generally around snack time in kindergarten, we learn to hold our cup with one hand, and this becomes just an instinctual movement. So anytime you grasp a cup, put your hand and your thumb around it, you lift it. There are infinite variations. The cup's of different size, different weights, different temperatures, and your brain adjusts to this effortlessly in executing this particular motor program. Well, the first thing we're going to look at the cortex and the basal ganglia to discuss, how this comes about at a motor circuit level, and then we'll look into motivated behaviors. So in the book, let's start at rest. So in the globus pallidus interna, substantia nigra reticulata, these GABA neurons are active. They're inhibiting this thalamocortical loop. And of course, the rest of the basal ganglia is also quiet. So you're either at rest or you are initiating some ongoing motor program, but at some point, your brain is going to want to change what you're doing. Either you're going to get off the rest state or you're just going to change the ongoing motor program. In that case, we look at the activity of the direct pathway. So the cortical neurons, glutamate cortical neurons, activate through the direct pathway. They stimulate these GABA neurons, which then release GABA into the GPI SNR. Cutting off this inhibitory flow then gives us strong activation in this thalamocortical pathway, and we get a very strong activation. Now let's contrast that with the indirect pathway that opposes the action of the direct pathway. So we have the cortical neurons, the glutamate neurons, activate the GABA neurons in the striatum. These happen to be dopamine 2-bearing GABA neurons. We'll come back to that in a moment. It will inhibit the globus pallidus externa, and when those GABA neurons are inhibited, the subthalamic nucleus will come to life. It will stimulate the GPI SNR, thus opposing the action of the direct pathway, and GABA release into this thalamocortical pathway will be increased and will then actually get a reduction in that strong force that was induced by the direct pathway. Now, normally, these pathways work together. They're both active simultaneously, and thus we get a smooth activation of a new motor program, as you can see in B. Now, what does dopamine do? Dopamine stimulates the direct pathway, and it inhibits the indirect pathway. So when dopamine is released and binds to the D1 receptor, this will be excitatory, more GABA, if it binds to the D2 receptor, that's inhibitory, less GABA. And so this input here is strengthened above what we saw on the last slide, and thus in a way dopamine helps initiate the movement. And this is why we spoke of dopamine as the go neurotransmitter. And obviously when you lose dopamine, as in Parkinson's disease, you will get bradykinesia. When you block dopamine receptors with antipsychotics, again, you will get Parkinsonian symptoms, because dopamine is really important in the oil of this mechanism of initiating new movement. And here, this obviously demonstrates the results of Parkinsonism, whether naturally induced by disease or through antipsychotics. We're blocking dopamine here. Now, the basal ganglia circuits are critical in initiating that new movement. Once the motor program is initiated, then the basal ganglia become quiet, and the corticocerebellar circuits are important in continuing the smooth execution of the movement. So the motor program is sent via the brainstem to the cerebellar cortex. The cerebellar cortex has extensive sensory input. So let's say I decide to drink a cup of coffee. I reach out to grab my cup and I lift it with a generic program, but my coffee cup is either full of coffee, it's not much coffee in it. As I get that vestibular input, I need to adjust the strength as I draw the coffee cup toward me. So that sensory input enters the cerebellar cortex, then is transmitted to the deep cerebellar nuclei, across to the motor thalamus, and now corrections to that motor program can be made. And of course, people who have cerebellar damage will develop an intention tremor. That is a tremor that is only present when they are actually executing the movement. And so as we initiate a movement at the cortical level, we get activation of the striatum. The GPI-SNR is inhibited, the thalamus is activated, and then this shuts off. The GP-SNR comes back online, and the cerebellum is active to execute that movement, take in the sensory information, adjust it, and then when we go to make a correction, the process repeats itself. And this happens over and over and over again as you initiate and continue billions of motor movements throughout your day. Now, what I've just described is the activity in the motor loop, which is responsible for most of the day-to-day movements that we make. But there are 4 other critical corticostriatal loops. We being visual animals, it's not surprising that there's one dedicated to eye movement. There's a prefrontal loop that's probably involved to some degree in the flexibility of our thinking. When do we move on to new thoughts? And then the orbital frontal loop and the cingulate loop, which are often subsumed under the term the limbic loops. Now, these, in particular, the cingulate loop is involved as part of the salience or limbic system. The ventral striatum, one of the reward centers of the brain, is involved in this particular loop. And that's what I'm going to focus on for a good part of this lecture. Now here's a little bit more detail in the circuitry of the limbic striatal loop. Here we have the orbital frontal cortex and cingulate. GABA neurons project to the ventral striatum. The glutamate neurons project here to the ventral striatum. GABA neurons then project to the ventral pallidum, and then to the thalamus. We have a corticothalamic loop, which is glutamate. This circuitry obviously is exactly the same as the parallel circuitry that I just described. Now, the input to the striatum is complex. We have the dopamine neurons from the ventral tegmental area, and we also have input from the hippocampus and the amygdala. All of these are going to influence the output of the ventral striatum. Now, the ventral striatum is active to a wide variety of rewards. So here we have individuals are doing a game where they're earning money. Here people are looking at pictures of beautiful faces. Here individuals are looking at sports cars. Here people are listening to pleasant music. Interestingly, we get big insula activation to music. Here people are looking at humorous stimuli. This is a study in which anxious people are given a placebo and they report a placebo effect. That is a decline in anxiety. When they get a placebo response or release from punishment, so to speak, release from pain, which is very rewarding, the ventral striatum is active. Here are individuals looking at pictures of their significant others. And in this task, people are engaged in altruistic punishment. That is, they think they're playing a game against an opponent. They're really playing the computer, and the opponent is cheating, and then they're given an opportunity to take revenge. And when they take revenge, this activates the ventral striatum. So as I've mentioned in prior lectures, the dopamine release into the ventral striatum occurs initially when we receive a reward, but over time the ventral tegmental area dopamine input occurs when we see the signals in the environment that predict the reward. So obviously money means we can go to the store and buy it. Now this one here in the middle upper panel, reward prediction error, we talked about that in prior lectures. That is when you are expecting a reward but it does not occur. And then we see decreased activity in the ventral striatum due to decreased amounts of dopamine entering the ventral striatum. And we'll come back to that when we discuss the habenula. Now let's look at a famous study, the Stanford Marshmallow Test.
Okay, sit in that chair. All right, here's the deal. Marshmallow for you. You can either wait, and I'll give you another one if you wait, or you can eat it now. When I come back, I'll give you another one, so then you'll have two. But stay in here and stay in the chair till I come back, okay? All right. I'm gonna go do something and then I'll come back.
It smells yummy. It smells really good.
Alright, so it's up to you. You can have it now or you can wait. Okay? I'll be back. Stay in the chair, okay? Okay. Alright, so I'm going to leave and then I'll come back, okay? So you can either eat it right now or you can wait. Either way, okay? Okay. How'd you do? Did you do good? You did? You wanted to eat it, didn't you? Yeah. So did I tell you to give you another one? Okay, now you can have both. You can eat them.
Now, you can see there's a slight age variation there. Like there were a couple girls there that were probably closer to their early 3-year-old birthday, and they just didn't have the impulse control to not eat. But the others, boys and girls, just had a whole variety of coping mechanisms to keep themselves from eating the marshmallow and delaying gratification. Well, this study was initially done, the marshmallow test was initially done with a group of kids in the 1960s, 1970s, and they have followed those kids up over the years, and their performance on the Stanford Marshmallow Test was surprisingly accurate at predicting long-term outcomes. People who could not inhibit as children, who ate the marshmallow quickly, tended to have lower SAT scores, did not go as far in college as their peers, even though these kids came from relatively similar socioeconomic backgrounds. And when they followed up these individuals in adulthood, they did functional brain imaging on them. And they had them do a go, no-go task, and here's the ventral striatum here. And what they found is the people who were high delayers tended to have lower activity of ventral striatal activity, and the people who were low delayers had higher activity. And they interpreted this as saying, well, if you've got a very active ventral striatum, it's driving you to reward. And those individuals thus, that's the reason they couldn't resist the marshmallow, because the ventral striatal system was setting up this drive for reward that they could not resist. And we want to keep this in mind because it's going to be relevant to our discussion of both depression, addiction disorders, and ADHD in subsequent lectures. Now here's another interesting study in this area. Video game playing has been long known to cause the release of dopamine in the ventral striatum in relationship to performance. So the bigger your ventral striatum, the better you are at video games. And other effects have been found in response to watching YouTube videos, texting, emails. Generally speaking, activation of our devices will activate the ventral striatum. So Lorenz and colleagues, a number of years back, took 50 young adults who were all video game naive. One has to ask where he found these individuals. But they were randomized to either a control group or to do a video game training group. And the groups then played 30 minutes a day for 2 months, and then they did a separate slot machine gambling task in the fMRI scanner, both at baseline and at the end of the study. And it will not surprise you that gambling tasks very strongly activate the ventral striatum. What they found at pretest is that the more you activated the ventral striatum, the more you were likely to experience playing the video game as fun. As you know from among your colleagues, there's probably a wide variation of people who just absolutely love their video games, talk about it, do it all the time, versus other people who kind of go, Well, at least in this sample, the stronger the activation of the ventral striatum, the more, as you can see in the lower right graph, they experienced it as fun. They then looked at the effect of training. So in the control group who got no training, there wasn't any difference in their ventral striatal activity pre-post, whereas there was in the training group. So, being exposed to video games, Perhaps you get training and you say, oh, now I can play. I can find the secret hammer or whatever it is that you're going after. This made it more fun, and we get greater activation of the ventral striatum. So you can see that the control group had some ventral striatal at baseline, but it actually went down post-training. In the training group, they maintained that activation of the ventral striatum. So again, this just indicates, that the ventral striatum is just programming itself for the level of reward in the environment. All right. So this gives us another more detailed view of the input to the ventral striatum. We're getting input from the salience structure, the other salience network structures, the ACC in particular, and we'll be talking about the ACC in subsequent lectures. We get input from both the amygdala and the hippocampus, and also input from the orbital frontal cortex. Next, we're going to focus on the input from the amygdala and talk about the amygdala in general. So the amygdala is quite a complex structure. Its input consists of activity from the insula, from the temporal lobe, particularly the fusiform face area. The amygdala can detect angry from non-angry faces at the fraction of the time that it requires for us to have conscious recognition of the face. The nucleus tractus solitarius, olfactory bulb, sex hormones, and so forth. So the amygdala is always informed about the physiologic state of the body, and it gets lots of input from norepinephrine, serotonin, and dopamine. Its output is also extensive. It has output to all of the cortical areas that it gets input from, important input to the hypothalamus, where it governs the output of the sympathetic nervous system and parasympathetic nervous system, direct input to the central gray and facial motor nucleus, where the freezing reaction in response to fear occurs when we say we are paralyzed with fear, and it creates facial expression. And indeed, controlling your facial expression when something sudden, either traumatic or exciting occurs is very difficult. You have to almost really work very strongly to inhibit facial expression, and that's because it's largely modulated at the level of the amygdala. And also the amygdala in turn will control the output of norepinephrine, serotonin, and the ventral tegmental area. Well, in the book, I give numerous examples of how the amygdala is activated. You should not think of it simply as an organ that detects threat, although it does have that is a subset of its functions. It's more important to regard the amygdala as a structure that detects biologically relevant stimuli in the environment. So some of the examples I gave in the book of the monkeys, so if the monkeys are in their cage and they're just given a water bottle, well, the amygdala will activate if the monkey is thirsty. In contrast, if juice is put into the monkey's cage, the amygdala will activate regardless of whether the monkey is thirsty or not, presumably because the tastiness of the orange juice is important. If you just put a rope in the cage, no reaction. If you put a toy snake, then the amygdala activates. So the amygdala is looking at external perceptions, matching it to the internal state of the body, and creating an output that is related to the drive. So if I'm hungry, food is important. If you're hungry and you walk by an apple sitting on someone's, sitting out there on the table in the call room, you're probably going to look at that. Your attention will be drawn to it. You may be tempted to eat the apple. If you just had a nice meal down in the cafeteria, you'll see it as an apple, but it won't create that same kind of drive. If you remove the amygdala bilaterally in monkeys, then you produce what's called Kluver-Bucy syndrome, where the monkeys can no longer recognize biologically relevant stimuli. So they can't tell pebbles from their food chow. They don't recognize sexual signals in their partners. And in humans who have damage to the amygdala due to a stroke, which is quite rare, they may also have difficulty recognizing emotional expressions. So again, the amygdala is an organ, a brain organ that recognizes biologically significant stimuli in the context of what's going on interior to the body, and then that information can be sent to the ventral striatal area, where it will probably gauge the amount of dopamine that's going to be released and perhaps have influence over the reward. Now, that's reward, but what about punishment, or more precisely, anti-reward? Well, we spoke earlier about the lateral habenula. Here you can see it from the lateral view, and you can see it even better from the posterior view. Here it is bilaterally. And I spoke to you about some of the inputs to the lateral habenula. It come from the pallidus, the nucleus accumbens, and the hypothalamus. And then the lateral habenula projects to the intrapeduncular nuclei, but more importantly, it projects to an area called the rostromedial tegmental nucleus, which in turn influences the VTA. And the lateral habenula, through this RMT connection, can turn off the ventral tegmental area. So here we see our inputs from various sources into the lateral habenula. They're in blue. So it comes from the hypothalamus, from the medial prefrontal cortex and the insular cortex, and then it projects to the VTA and projects to other areas. But again, here's this projection to the RMTG back to the ventral tegmental area. Well, let's take a look at this fMRI scan. Here under nucleus accumbens, and remember that term is somewhat the same as the ventral striatum. This is a summary of studies of people responding to rewarding stimuli. And we can see again, as we spoke earlier, we get strong activation of the accumbens. Now the habenula, this is a summary of studies of people reacting to punishing stimuli or adverse stimuli, or studies where reward did not appear. And there you can see that when the habenula is very active under these circumstances. So I spoke to you before about reward prediction error, and the example I gave is that you're going to the machine when you're on call to get, a bag of candy or something. You put your money in, you see the little thing turn, you're expecting that candy to drop, and it gets stuck, and you can't get it down, and you have that sense of dysphoria and disappointment. That's a reward prediction error. The reward is not there. Well, probably your prefrontal cortex, your insula, these areas perceive that we are not getting our reward, and that will trigger the lateral habenula, which will shut off the VTA, a drop in dopamine, and perhaps that underlies the negative reward experience. And again, we will come back to that when we discuss both addiction disorders and depression.